Hi everyone. Can you see my slides? Yeah. Okay. So, hi everyone. First, thanks to the organizer for inviting me for this seminar. Um, I am Viviana Pezzotta, and I'm a second year PhD student at the University of Milan, mainly working with Stefano Facchini and Giuseppe Lodato on a multimolecular approach to gas kinematics to have a deeper characterization of the 2D pressure structure of disks. So, just a brief introduction. We all know that planet formation takes place inside cold rotating molecular clouds that undergo gravitational collapse and form systems composed by a central protostar surrounded by a protoplanetary disk, which is composed for the 99% of its mass of gas and just for the 1% of dust. Then this system will evolve, giving birth to fully grown and mature planetary systems like our own. But we all know that in order to really probe and understand the mechanisms that lead to planet formation, it's very important to study these systems in this particular phase when planet formation is occurring, so it's still ongoing. Now, these disks have been recently observed by many surveys, both in the dust continuum and in the gas emission. You can see here on the left the D-sharp survey in the dust, and on the right the MAPS survey in the gas emission line. Um, and these disks have been observed in different frequency ranges and with different techniques. For example, in the infrared light, in scatter light, but also in the dust thermal emission and in the gas line emission. I am mainly interested in using interferometric ALMA data in the millimeter and submillimeter regime to study these disks using molecular gas line emissions. So in my field, which is gas kinematics, is the field where I'm mostly working on. And this is a recent field, let's say, that has whose goal is to study the gas velocity field using emission lines. And the main aim is to probe the disk properties and the mechanisms that lead to planet formation. Now, the great potential of gas kinematics has already recently led to some key results about many topics. For example, the detection of molecular winds in disks and kinematic signatures of the presence of embedded planets in disks. But also we had some indications of the presence of gravitational instabilities, and we have dynamical measurements for stellar and the disk masses, and much more. What's important here is that using these kinematics, we can really study whatever phenomenon that leaves an imprint in the gas velocity field. So as for the observation, gas kinematics require high spatial and spectral resolution, which is why we use ALMA data in the first place. And for each line, the end product of the observing process is a data cube that you can see here. So a cube with two spatial axes and one spectral axis, which is frequency, and of course it might be linked to the line of sight velocity through the Doppler effect. Now, from this data cube, we can have channel maps that represent the line emission along the disk in different velocity or frequency channels. And this peculiar butterfly shape you see here in this example is the typical morphology of line emission in a disk where the gas rotates at a Keplerian speed. Now, from this data cube, we can also just collapse the cube on a spectral axis, and we can obtain line of sight velocity maps like this one you see on the right. And again, the blue and red lobes represent the Keplerian rotation of the disk. And finally, from this data cube, we can extract a rotation curve, which is the radial profile of the gas rotation velocity. And this is the main tool I've been using. And as I will show you in this talk, rotation curves are powerful tools to study the disk properties. So in my work, I've been mainly focusing on this very famous and very bright source, HD163296, that you can see here in the gas emission of 12CO221 line, and also in the millimetric continuum in the dust. About the extraction procedure of these curves, we can say that in every pixel of the zero momentum map, there is a spectrum that we fit in order to get the line centers, so the velocity corresponding to the intensity peak. And we do this for all of the spectra that are inside of this annulus of fixed radius. And by doing so, we get a sequence of line centroids that we fit with the sinusoid function to get the rotation velocity of the gas at a specific radius. And then by doing so for all of the radii, we get the whole rotation curve. Now, as you can see here, the rotation curves are given by the sum of different contributions. So a first term, which is due to the stellar gravity and it's linked to the mass of the star. Then we have a second term, which is due to the pressure gradient along the emitting layer of the molecule we're considering, which is linked to the disk scale radius. And then finally, we have a term which is linked to the self-gravity of the disk and depends on the disk mass. Now, the interesting thing is that by fitting rotation curves with an appropriate model, we can have information on the stellar mass, the disk mass, and the disk radius, and also we can get insights on the 2D pressure structure of disks. Now, why we're interested in the pressure structure? Well, because we know that pressure is a fundamental quantity for disks for many reasons. For instance, the gap dynamics is affected by pressure support, while the dust dynamics is regulated by dragging. And also, we know that dust rings are often collocated with pressure bumps, meaning that pressure trapping could be an efficient way to form dust substructures. And finally, we know that pressure is strongly linked to gas density and temperature and thus influences this chemistry. Now, about the fitting procedure of these rotation curves, we can say that usually in the fit, we assume a vertically isothermal model for the disk, where temperature only varies with radius. And we usually fit just one or maybe two rotation curves simultaneously. Now, what I've been trying to do with my work is to try and tackle two main questions that are, how does the pressure term change in the first place if we consider a non-isothermal model for the disk? So a temperature that also varies with the height above the midplane Z. And this would imply to include thermal stratification in our model. Second question is, how does the simultaneous fit of rotation curves improve with the number of fitted lines? So does the multimolecular approach actually work? So as I was saying, instead of using the usual vertically isothermal model for the disk, we adopted a vertically stratified model where both temperature and density are equal to the ones on the midplane multiplied by these two functions f and g that depend on both r and z. So as a consequence, also pressure will depend on both r and z according to the product of these two functions. And this represents an additional pressure contribution to the rotation curve. So basically what happens is that the thermal structure modifies the pressure term, which leaves an imprint in the gas kinematics that we can measure by fitting rotation curves. So what do we need to know for our model? Well, first, we need to know the 2D thermal structure of the disk to get the right expression for the F function. Then we need to solve the vertical hydrostatic equilibrium equation to get the right expression for G, which is linked to F, so to the temperature. Then we need to assume a disk surface density to have the density on the midplane. And finally, we need to know the emitting layers of the molecules we're considering. Why we're interested in a multimolecular approach? Well, because we know that distinct molecules emit from distinct regions in the disk. So as you can see from this plot, every molecule emits from an intermediate gas layer, which is located between the hot disk surface, where a molecule photodissociate due to the UV photons of the star, and the cold disk midplane, where molecules can freeze out onto the dust grains. So using different traces allows us to probe the 2D radial and vertical extent of the disk. And in particular, I'm using the 7 traces you see marked in color boxes in this plot on the right. So this is just a general workflow of the results I'm going to show you. So first, I'm going to show you a preliminary test we did to check the validity of the emitting layers we're assuming for our molecules. Then I'm going to tell you about the rotation curves extraction and how we fit them all together with a multi-molecule fit using a thermally stratified model. And finally, I'm going to tell you what we can really say about the 2D pressure structure of this disk. So let's start from point number one. As I was saying, for this analysis, we need to assume both temperature structure and the molecular emitting layers. So as the first thing, we did a complementary test to check the validity of the emitting layers we're assuming once given thermal structure for the disk. And we did this by computing the optical depth of some lines. Why? Well, simply because the optical depth of a line is easily related to its emitting layer. So once we can measure the surface brightness from data, and we know the temperature and the molecular emitting layer, then we can have a profile for the optical depth of a line. So we did this for 4 lines, and here are the results, which are consistent with other independent estimates of the optical depth of these lines. So at this point, we benchmark the validity of the layers we're assuming, and we can go on with the extraction of the curves and with the rest of the analysis. Also, we stressed this is a very straightforward method to get the optical depth of the line when just one line is available, and there is no need of chemistry or excitation temperature studies. Now, some of the traces, namely C2H and HCN, you see here, show hyperfine transitions, meaning that the spectra have 2 or even 3 intensity peaks, as you can see here. So we implemented in the standard routine codes a new method to be able to properly fit the spectra. And by doing so, we got a big improvement in the extraction of the rotation curves. Here you can see a comparison between the red line, which is the C2H rotation curve we got with our new method, which is pretty smooth and has small errors if compared to the blue line, which is instead the rotation curve of C2H we got with the previous method. So in this way, we can really do kinematics with hyperfine lines, and we also gain both precision and accuracy in this way. Now let's focus on the emission of molecules that have a strong intensity gradient in its emission, like the C2H you can see here, and you can also see it in the intensity radial profile of this molecule. So if you look at the rotation curve of this molecule, it's the pink line here, you will see some deviations if compared to the green line, which is instead the rotation curve of the 12CO, so a molecule, as you can see, with no strong intensity gradient. And problem is that these deviations we see in the rotation curve of the C2H are not real, but they're due to an observational bias called beam smearing. So as we extract a single spectrum from inside a resolution beam, that spectrum is actually the intensity weighted average of all of the spectra that fall inside the beam. So if there is a strong intensity gradient across the beam, then velocities will be biased, and we will measure deviations in the corresponding rotation curve. Now, if you look at the blue line, these dots are just the difference between the 2 rotation curves. And this line shows an opposite behavior with respect to the orange line, which is instead the intensity gradient of C2H. So from this basically perfect anti-correlation, we can really say that the deviations we measure in the C2H rotation curve are just apparent, and they're not linked to the presence of additional pressure effects that might be linked, for example, to the presence of gas density fluid structures. And also, in this case, additional pressure gradients would induce deviations of the opposite sign. So again, we have to be careful when interpreting rotation curves of molecules that have strong intensity gradients in their emission. Now, once we have our 7 rotation curves, we can fit them all together with a thermal stratified model you can see here, with the different contributions coming from the star gravity, the pressure gradient, and the self-gravity of the disk. And this is the additional term due to thermal stratification of the disk, as you can see, depending on F and G. Now, I'm not going in detail on the model, but this expression depends on 3 fundamental parameters that are stellar mass, the disk mass, and the disk radius. So when we fit our curves all together with this model, as you can see here in the plot on the right, we also get dynamical estimates for these 3 fundamental parameters. Now, we wanted to check if a multimolecular approach actually works. And to do so, we computed the chi-square as a function of the number of fitted lines. And as you can see, we get the major improvement by adding the C18O as a third tracer. And by doing so, we also got improved estimates for the disk mass and scale radius, with differences that go up to the 10%. And also, you can notice that the chi-square keeps decreasing by increasing the number of fitted molecules. And this is good because it means that a multimolecular approach actually works. At this point, we can also get a 2D pressure map of the whole disk. And as you can see, the normalization term depends on the three just found parameters, while the shape of the profile depends on the thermal structure. And as you can see from this plot, using multiple traces that you see marked in colored lines, really allow us to trace the 2D pressure structure along a wide radial and vertical ranging disk, which is what we are interested in. Now, how can we really say that a stratified model is better than the isothermal one? Well, if you look at the blue dots, these data are just a difference in rotation velocity between the C18O, which is pretty close to the midplane, and 12CO, which emits in the upper layers instead. And the problem here is that we cannot explain these discrepancies we measure in the rotation curves of these two lines with an isothermal model. Because as you can see from the green line, the isothermal prediction is completely wrong. But a stratified model can actually explain the mean behavior of this quantity much better. And this means that the discrepancies we measure in the rotation curves of different lines are linked to the thermal stratification of the disk and not just to the different emitting heights of the molecules. And also, I'm showing you this plot about C18O and 12CO, but actually, we see the same effect also with other traces, meaning that the 2D pressure structure has a strong impact on gas kinematics across the whole disk vertical extent. And finally, in this data, you can see some small-scale oscillations that are due to the presence of additional pressure effects that might be linked to the presence of dust substructures we're not considering in a model. But anyway, these additional pressure effects are imprinted in the gas kinematics, and they have different amplitude at distinct heights. And this would point towards a 3D structure of gaps. Now, as a little bonus, we wanted to check the dependency of our results on the assumed emitting layers. So we repeated the same analysis, this time with non-parametric layers for all of the molecules. And as you can see here, this is basically the same plot I was showing you before, but this time assuming non-parametric layers for all of the lines. And basically, we get the same trends, which is very good because it means that our main results do not depend on the chosen parameterization for the molecular emitting layers. And by doing so, we also obtain these differences you see here for the three fundamental parameters. And as you can see, the disk mass is the one which is more affected by this kind of systematics, which was expected and in agreement with some recent papers that studied the impact that systematics have on the dynamical estimates of these parameters, and in particular on disk mass. Now, we show that the thermal structure has a strong impact on the gas kinematics and also on the pressure structure in disks. So at this point, the natural question is, how does the thermal structure impact the dynamical measurement of disk masses? So we can get a dynamical estimate for the disk mass by fitting two or even more lines together, emitting from distinct emitting layers in the disk. And by doing this, if we have two or more lines, we can have information on the 2D temperature structure of the disk, so we can take into account the vertical thermal stratification of the disk. But yet, we can still get a dynamical estimate for the disk mass fitting only one bright line, usually a 12CO221 line, which is the one we observe the most and we can find in the archive. But in this case, we have no information on the 2D thermal structure of the disk, so we have to assume an isothermal model for our disk. And the natural question at this point for me was, how do these estimates compare? So to answer these questions, I run some preliminary tests on the sources of the ALMA-large program maps, which are 5 disks. And you can see in this plot, the blue dots are the dynamical estimates I got for the disk masses of these sources by fitting two rotation curves together, so 12CO and 13CO221 lines, and taking into account the thermal stratification of the disk. While the orange dots are the dynamical estimates for the disk masses that I got by fitting just one rotation curve, so the 12CO1, and assuming an isothermal model for the disk where the temperature is equal to the brightness temperature along the 12CO layer. And then you can see we get a pretty significant discrepancy for all of the sources that you can also see in this plot where I'm just showing the difference between the two obtained estimates normalized by the mean for every source. So what we can say from this preliminary test is that the 2D thermal structure we can access from multiple line fitting is required to have more reliable estimates for the disk mass. So I will leave you with my conclusions. We can say that our multimolecular analysis of rotation curves showed us that thermal stratification is indeed important across the disk vertical extent, and that a multimolecular approach improves the dynamical estimates we have for the stellar mass, for the disk mass and the disk radius, and also that the 2D pressure structure can be really probed and measured using multimolecular kinematics. And with this, I am concluding. Thank you for your attention.
Thank you very much. That was a fantastic talk. Thank you. Does anyone have any questions that they'd like to ask? I'll start out with one that I was thinking about. So you have a few parameters that you throw into your thermal stratification model, like your disk mass and radius and so on. How do you decide on what mass and radius to use initially?
You mean for to use in what exactly?
So the model for your thermal stratification model, when you have to input a mass and a radius of your disk, because there could be some uncertainty around certain parameters like the radius and the mass of a disk. How do you decide on which one to use in the end? Yeah, for this part.
Well, you fit for those parameters. You don't need to decide in advance. So this is the model you have, and just the model itself depends on these three parameters. So what you do is you have your data, which is the rotation curve or several rotation curves in my case. And then you just fit all of the curves together with this model. And by fitting these curves, you get the best fit model, the best fit parameters for these three parameters I was highlighting here. So you get these best fit values for stellar mass, disk mass, and disk radius. So you don't need to decide in advance. You just fit for those parameters.
Good. Okay, that makes sense. Yeah, thank you.
Thank
you. Yeah, question from Richard.
Thanks for a really nice talk. Do you hear me okay?
Yeah.
Yeah, great. So I think it's really nice that you're showing that adding all of these extra traces gives you better constraints on things like the disk mass and the stellar mass, and that all makes sense. I didn't really understand, though, why adding more data makes the reduced chi-squared go down. That seems somewhat counterintuitive to me. Is there more to say there, or?
Yeah, it's this plot. Well, the main point at the beginning when I began this analysis was to understand if adding data and adding many molecules could help the fit procedure, or maybe it could lead to problems and have to difficult results maybe that you can't really interpret because you have a lot of data and you're adding a lot of points in your fit. So we wanted to check if this was good and it was going to improve our analysis or make it worse. So I just tried this, and honestly, I can say that what really matters for what I saw in my analysis is to have, first of all, reliable data. And as you can see here, adding the C18O allow us to get a big improvement in the extraction of the dynamical measurements of these parameters, from what I can see. And then you can just go on with adding some molecules if you have if you're comfortable with the rotation curves you extracted. I think that at some point, if you have rotation curves that are not really reliable, maybe because the line has a low signal to noise ratio, then at this point, your fit gets worse if you keep adding molecules. But if you have reliable curves and good quality data, as I had in this case, because this was maps data, I think that adding points in your fit just makes the fit better. And to test it, I just computed the chi-square because I wanted to have a quantitative way to see this.
Thanks.
Thank you.
Has anybody else got any further questions that they'd like to ask? I've one more follow-up, sorry, just on the question asked earlier in that case. Have you done a comparison of the masses that you retrieve for example, HC 163296? Have you compared that against other methods of measuring the mass and see how that compares?
Yeah, I don't have a backup slide on it, but yeah, I did the comparison. I know that there are many recent papers from 2019 on that try to estimate the disk mass for this source. And actually, the results are pretty consistent because they go from, let's say, 0.1. I will show you here. This is my best fit values. And they usually go from 0.1 to 0.2. This is the maximum estimate I saw in the literature. And this estimate, they are obtained by using different methods. For example, by fitting optically thin tracers, by using chemical codes. There are some papers also in the MAPS collection, and some recent papers from Paola Martir, for example, or Lucas Staffer, that calculated, the disk mass for this particular source, but they're pretty consistent. So I think it's a good result also because the dynamical estimate and in general, the estimate for these masses is really hard. So if you obtain a result which is within a factor of 2, that's already a good result for what I know. So they're pretty consistent.
Okay, great, cool. Thank you.
Thank you.
Okay, thank you, Viviana. Excellent talk. I think now we will move on to Cristiano, who is